In this video, we look at the 2008 higher level particle physics question. So again, it throws up a few interesting twists and asks a few different kind of things. So the question first off says, baryons and mesons are made up of quarks and experience the four fundamental forces of nature. So that statement then breaks down for the first 20 marks. So first they ask, list the four fundamental forces and state the range of each one. So we have our four forces here: strong nuclear, electromagnetic, weak nuclear, and gravitational. The range of each then is given at the side. If you don't like remembering 10 to the minus 15, there's a prefix for that which is called the femto. Femto is 10 to the minus 15 meters. Both the electromagnetic and gravitational are an inverse square relationship, so it's 1 over r squared. As the radius doubles, the range will be 1/4. The weak nuclear force is 10 to the minus 18, which is known as atto. So if you prefer to remember a word, strong force F for femto, and weak nuclear is A for atto. And the other two then match are infinite. So this is 1, 2, 3, 4, 5, 6, 7, 8 marks. The next thing they say is name the three positively charged quarks. So the three positively charged quarks are the up, top, and charmed, and they all have positive 2/3 charge. Then they say, what is the difference in the quark composition of a baryon and meson? So typically it's a good idea to give the definitions anytime you're asked one of those things. So a meson is made up of any one quark and any one antiquark, so that's your meson, 1 and 1, and a baryon is made up of any three quarks. So mesons have 2 bits that make them up, and baryons, the bigger ones, have 3 quarks. The last bit then is they ask the quark composition of the proton, and the quark composition of a proton causes a positive charge. You could have an up, up, down. So up is 2/3 plus 2/3, and then a down, which is a negative 1/3. So that gives you an overall positive of 1. So any three quarks which give this relationship is fine. Up, up, down is your proton. So they move on then into accelerators. So in a circular accelerator, 2 protons, each with a kinetic energy of 1 giga-electron-volts, traveling in opposite directions, collide. After the collision, 2 protons and 3 pions are emitted. They ask, what is the net charge of the 3 pions, and then justify our answer. So if you look at the reaction here, we have a proton plus a proton which smash together. They create a proton, and 3 pions. Now we know a proton has to be plus 1, so we have plus 1 and plus 1 on this side, which will give us plus 1 and plus 1 on this side. So in a nuclear reaction, charge has to be conserved, so these 3 overall must be neutral, because the net charge before equals the net charge afterwards. So they could be 3 neutral pions, or they could be a plus and minus and a neutral, but overall charge must be conserved, so the net charge is 0. The next bit then is they ask us a calculation. So we need to get the maximum number of pions that could have been created during the reaction. So they have 3 in this case, but there could have been more. So what we need to do is get first off the combined kinetic energy and then the maximum number. So first is the combined kinetic energy, so we get our formulas down. E equals mc squared, and our kinetic energy of Ek is equal to a half mv squared. So please, on the next page, at the bottom of the question they give us a lot of these figures. So sometimes they do give you information at the bottom, sometimes they don't. So these are all listed at the bottom. So that's the charge on the electron, that's the mass of the proton, that's the mass of a pion, and that's the speed of light. So we have all of those. This then is given in the question, so that's in the first sentence, which often you can scan over and forget about. It says, in a circular accelerator, 2 protons, each with a kinetic energy of 1 giga-electron-volts. So again, you got to be careful. Each of them has 1 giga-electron-volt, so we got to double that. So that gives us 2 giga-electron-volts, and giga is by 10 to the 9. So we have that much electron-volts, so that's what we'll start off working with. So the 3 pions created are mass, each one of 2.4842. So we triple that, so we get this here. So that is our overall mass that's created. So we switch this then into the E equals mc squared. So we have our combined created mass. I worked combined rather than singularly. So we have a combined mass multiplied by the speed of light squared, which gives us this figure in joules, which I round off in this case. Again, you can keep kind of working with figures. So the energy then, I need to get that into joules. So this is the energy that's created from the 3 pions. So this much energy we needed to create those. So in order to compare it, I need to get it measured in electron volts, so I can match this one up here. I could change the electron volts into joules either, I just went this way. So this is our energy in joules. So we convert that by multiplying by this factor here. So that gives us our electron volts. So that's 4.18047 by 10 to the 8 electron volts. So that much energy was input and then turned into it. So we have, this is the energy required to make our 3 pions. But overall, we have more energy put in. So that extra energy would appear in this reaction up here, or the one on the previous slide. It would appear for these 3 as kinetic energy. But it could also have been used to make extra particles, extra pions. Just as a recap, we have our 3 pions. They would make this much energy, or be made from this much energy more precisely. So it requires this much energy to make the 3 pions, and the rest will turn to kinetic energy. So kinetic energy of the protons is this 2 by 10 to the 9 electron volts, so we get the difference. So this much energy has been left over. So that's our first part finished. That's our kinetic energy of the 3 pions. So that's the kinetic energy of the protons. That's the energy going in. This is converted into mass, so this is the amount of energy left over, which would be kinetic energy. Then the second bit is they ask us for the maximum number of pions that could have been created during the collision. So the energy needed to create 1 pion. So that's the mass of 1 pion multiplied by the speed of light squared. So that's this much joules, and then I round it off. We convert that number in joules into electron volts. So I have 1.3935 by 10 to the 8 electron volts. So that's needed to make 1. Overall going in, I have this number, 2 by 10 to the 9 electron volts. So I divide one by the other, and I get this number here of 14.35. So the max number then is 14. You can't have 0.35 of a pion, but you would always round down. Even if that was 14.95, you would round down. Just like you can't have 0.35, you can't have 0.95, or you can't have 0.99 either. So you will always round down in these things because it's either created or not. That's similar to when you're looking at your interference pattern. If you're looking for the maximum number of dots that could appear on a screen, you'd always round that one down too, because you can't have a fraction of a dot. It's there or it's not. So that's the end of this question. Again, a good bit of calculations. Those calculations were 24 marks, and there's a good bit of work in them. But it's a typical thing. You have this much mass, which from this much energy. So then you get that's your kind of background work. Then you get your kinetic energy, and then you can finally figure out your number of ions.